In this video we're going to consider the intersection of three planes. Now then, if you're sitting in a room, the room's probably got walls, and if you look at two of the walls you'll notice they probably intersect, and they'll intersect at a line. That is, of course, unless the two walls that you're looking at are parallel to each other. So if we have two walls or two planes that are going to intersect, they're going to intersect at a line, and previously we've seen how to solve that. Now if you've got a third wall and you see where perhaps the ceiling intersects with the two walls that you're now looking at, those three should intersect at one point. And there we can see 1, 2, 3 planes there intersecting at a point here. So when we're asked to solve the intersection of three planes, provided that they do intersect, then they'll intersect at one point. If you remember previously, two planes will intersect at a line as long as they're not parallel or coincident. So if you've got three planes, all you're really doing there is taking one pair of intersections, in other words a straight line, and then another pair of intersections, so that would be another straight line, and therefore seeing where those two lines would intersect. Just remind you about the equations that we've had for intersection, or for the equations of planes. So the first one, the vector equation of a plane, is this one. We've got the normal form, which is very useful, which is really no different to the Cartesian form, and that's the one that we're going to deal with today. So the first example that we're going to consider here is the intersection of three planes where they do intersect at a point, and they give us what we call a unique solution. And what I want to do here is give you a method for solving this. So you should be pretty comfortable with solving simultaneous equations with two unknowns in. So two simultaneous equations with two unknowns and finding a solution for that. This one involves a little bit of work because first of all there are three unknowns, x, y and z, and three equations, of course. So here's the method that I use. Just a little side issue on that actually while we're there. This lesson is for the IB higher level mathematics course, and in the current syllabus there are no matrices in that, and there is quite a nice method for solving simultaneous equations using matrices. Now there's nothing wrong with you studying that and finding out how to use it yourself, but as it's not on the course, I'm not going to show you that here in this lesson. We're going to use an algebraic method to solve it. Okay, so the first thing I do here is that I'm going to label up my three equations. Now this method is not at all difficult, but what it requires is for some very, very careful manipulation. Now my method is as such. What I'm going to do is I'm actually going to find the intersection of two of the planes and find the line where they intersect, and I'm also going to find the intersection of the other two planes and find where the line where those two intersect, and then I'm going to try and find the intersection of those two. So here's my method. First of all, I'm going to combine the first equation with the second one so that I can eliminate z. Now to be able to eliminate z, what I'll need to do is multiply the whole of the second equation through by 2, so that I get 2z here, and I'll be able to subtract them. So what I could do is equation or two lots of the second equation subtract the first one. So if I get 2z here, and I can do that, and I will get 3x subtract 3y is equal to 12. Now I say I could do that. That involves me being really quite careful with the calculations that I'm doing, and sometimes it's preferable just to write these out. So what I mean by that is I'm just going to rewrite equation 1 out again, x plus y plus 2z equals 0, and then I'm going to write the second one out again, or double of the second one. So I'll times everything through by 2, so that's 4x minus 2y plus 2z is equal to minus 12. And I just think if I do it this way around, then I'm less likely to make a mistake. So let's try this now. So I'm going to do the second equation, subtract the first one, 3x minus 3y, that's where the z's cancel out, and there we go, I've got minus 12. And that's a really good demonstration there of doing it all in one go. It's really easy to make a mistake, as I just did there. So as I say, my preference is just to take my time with this and write those equations out again, and let's really make sure that we get them right. So I've combined 1 and 2 together to now give me an equation just in terms of x and y. I've eliminated z from my equation. Now what I'm going to do is take two other equations, so number 2 and number 3, and then combine those together to eliminate z as well. So this one looks a little bit easy because I've got z here and minus z, so just doing 2 plus 3 here will allow me to eliminate z. So 5x plus 3y, the z's cancel out, is equal to minus 12. So we have gone from having 1, 2, 3 equations with 1, 2, 3 unknowns to 2 equations and 2 unknowns. So this looks similar now to the simultaneous equations that you might have solved previously in perhaps just 2 dimensions. So if you like labelling these up, that's a good idea there. I'll call that one A, that one B, and then it looks easy, doesn't it? Let's eliminate 3y from that by adding the 2 equations together. So if I do A plus B, that'll give me 8x is equal to minus 24, which means that x is equal to minus 3. In other words, for the intersection of the 3 planes, the x coordinate of that is at minus 3. What we've got to do now is find the y coordinates for that point and the z coordinate for that point. So that's really simple. All we've got to do is substitute that value back into one of these equations here and solve for y. So let's use 3x minus 3y equals minus 12. So that's minus 9 minus 3y equals minus 12. So that means 3y is going to be equal to 3, y equals 1. So I've got my x coordinate, my y coordinate, and now I want my z coordinate. Well, let's pop those bits of information into this equation here. So I've got x plus y plus 2z equals 0. So x plus y plus 2z equals 0. Now a space here, but that is going to give me z is equal to 1. So what that means is that we've got a point of intersection at minus 3, 1, 1. Right, let's just see how that looks graphically. So here we are, here are the 3 planes. That's the first, the second and the third there, and that's our point of intersection, which is at minus 3, 1, 1. So that's what we call the unique solution of simultaneous equations. In this case, the planes there meet at one point. Right, that's the first case, and that's the nice simple case, probably the most satisfying, that we get a point. But that's not all the possibilities. So we've already spoken there right at the start of the video about planes not actually meeting in the first place. So what we're going to do now, or what I'd like you to do now, is think about the other possibilities. Now, there are some possibilities where planes will just not meet at all, and there'll be other possibilities where there'll be an infinite number of solutions. Now, what I would like you to do is take 3 pieces of paper and try and find all 6 of these other possibilities. So we've done the first one, 3 planes meet at a point. There are 6 more. what I'd like you to do is try and find the 6 other more, and I'll give you a clue here that there are 4 where there are no solutions at all, and there are 2 where there are an infinite number of solutions. So pause the video now, get your paper out, and try and find those and to describe them. And I'll come back with the solutions in a minute. Okay, welcome back. So here are the 6. First of all, let's start with 0 solutions. The first, we sometimes call this, is where the equations are inconsistent, and you'll see in a second why that's the case. So the first possibility is where they form a kind of prism. So 2 of the planes will meet at a line, 2 other planes will meet at a line, and the third pair will meet at a line, but there's no point where those 3 lines will meet, and that's often called a triangular prism of planes. So there's no solution to that. There's no unique solution. There's no point where all of those 3 planes will meet. So that's the case number 1. The second one, you could have 2 planes that are parallel. So these 2 horizontal planes here are parallel to each other. They're going to never meet. However, what you could have is a plane that passes through those 2 other planes. So like before, this plane here and this horizontal plane will have a line intersecting, and this plane here and this plane here will have a line that's intersecting, but they will never meet at a point. So again, that will give us an inconsistent set of equations when we come and try and solve them. The third case is where we've got 2 planes that are coincident, so basically one lying on top of the other, and then a third plane to that which is parallel. So the first 2 planes here are obviously going to meet, and there will be an infinite number of solutions to that, but they will never ever meet with the third plane. And the final case for 0 solutions, which I'm sure you've got, is that all 3 planes are parallel. Right, so what about the other case, or the other cases? So this is where we've got an this is where we've got an infinite number of solutions. So we could have 3 planes meeting in what we call here a sheaf of planes. So they meet, and they will meet at a line there. What we could do if we're trying to solve this is find the equation of that line. So it's not one point, but it's an infinite number of points along that line, hence why we call it an infinite number of solutions. And the second case, did you get this, is where all 3 planes are coincident. So all 3 planes coincide, they will give us an infinite number of solutions. So what we're going to do for the remainder of the lesson is to look at the 2 other cases. In other words, where there's going to be one solution where there's no solutions at all, the equations are inconsistent, and the other type is where there's going to be an infinite number of solutions. So if we were to solve this set of equations here, this system of equations, that would give us one of the 2 examples I've just named. Now before I give you the answer to this, what I'd like you to do is to pause the video and just try to solve the equations as we've just done for the first 3 and see what happens. So what I mean by that is take a couple of the equations, eliminate one of the variables, and take another couple of equations and eliminate one of the other variables, and just see what happens with the 2 equations that you get. So pause the video now and try and do that. Okay, welcome back. If, like me, you try to eliminate z using equations 1 and 2, you will have got the equation 5x minus y is equal to 13, and eliminating z from 2 and 3 by combining those gives us the equation 5x minus y equals 13. So where do we go from there? Well, there's not a lot we can do with that in terms of finding a unique solution. Why? Because there isn't one. So just forget the context of this problem for a second and imagine that I gave you these two simultaneous equations and I said solve them. You wouldn't be able to find a unique solution, and if you considered that graphically, what you'd have is two lines that would be lying on top of each other, two identical lines. So we've got an infinite number of solutions there. So if by eliminating one of the variables from your three equations, you get this sort of situation here where the two equations that you get are exactly the same. Now one could be a multiple of the other, so I could have 10x minus 2y equals 26, but that's obviously exactly the same as the previous one. There's no way you can go any further with that to find a unique solution, because there isn't one solution. There's an infinite number of solutions. So how do we go from there? How do you find the line of the equation? Well, you could use your calculator, but we should be able to do it algebraically. And if you can't remember from a previous video, I suggest you look back at the video where I showed you how to find the equation of a line where two planes intersect, and it's exactly the same method. So go back to that and find the equation of the line for this case. Now then, which type is it? So for an infinite number of solutions, it's either a sheaf of planes or all three planes are coincident. Well, in this case, do all three planes coincide? Are they actually the same plane? Well, of course they're not, because they're not parallel to one another, and we can see that from the coefficients of the x, y and z terms. So if they're not parallel to each other, then it must be the first case. That must be a sheaf of planes. Let's just consider that on autograph for a second. That's how it would look. Those are the equations of the three planes, and they meet there at a straight line. So if we're asked to solve this system of equations, what we'd be asked to do in effect is to find the equation of the straight line there. As I said, I'd like you to try and do that and refer to a previous video if you need some extra help with it. Of course, your calculator will do it. If you put them in, it will give you in that kind of strange form there that we've seen before. Right, let's have a look at the third case then. So you can probably guess, given that that was an infinite number of solutions, the next one I'm going to give you to look at here is going to give you zero solutions. So as before, I want you to pause the video and try and solve it for yourselves algebraically, and just to see what happens. Have a go at that, and I'll come back with the answer in a second. Okay, welcome back. You'll notice with these equations that they're just a slight variation on the first two systems that I gave you, and you probably see why I could adapt those to give them zero solutions or infinite number of solutions. Anyway, if you did the same thing, which I'm sure you did, and you combined the first two to eliminate z, and then the second and the third one to eliminate z, then the two equations that you will have got would be 5x minus y equals 13 and 5x minus y is equal to 15. So if you combine them in a different way, you'd have got maybe y's in terms of z, but a similar situation and a similar problem to solve. So hopefully you got stuck at that point there, because if you're trying to solve these simultaneous equations, and the first one here is telling us that 5 lots of x minus y is equal to 13, then how on earth can 5 lots of x minus y be equal to 15 as well? It can't. And if we were thinking about simultaneous equations with two unknowns and what would be straight lines in 2 dimensions here, what we'd have on the graph would be two lines that would be parallel to one another. So there's no way that those lines are going to intersect. So this is, in fact, as we've just said before, a case where there are zero solutions. Those two lines don't intersect, which means that these three planes don't intersect either. So which of the cases is it? We've got a triangular prism of planes, we've got two planes being parallel and one distinct, two coincident on one parallel, and three parallel. So have a look at those equations, look at the gradients of the normals, and try to decide which of the four cases it is. Okay, welcome back. So what you might have decided then that it must be a triangular prism of planes. Why? What's the reason for that? Well, for any of the other three possibilities there must have been two at least of the planes parallel to one another, and that clearly is not the case. If we look at the directions of these planes here, the normal vector for this one is 1, 3, minus 2, this one is 2, minus 2, 1, and this one is 3, 1, minus 1. And those, you can't take any of those two there and find one of them to be a multiple of the other. In other words, the normals are just not parallel to another. So there's no cases there where there's two, never mind three of the planes parallel, so it must be the triangular prism of planes. So then, when I'm trying to solve a system of simultaneous equations with three unknowns, or we're considering three planes, then there are three possibilities. We could have a unique solution. In other words, in terms of the planes, they will meet at a point. And if you try and solve it algebraically, you will get that unique solution. You'll get a point. The second possibility is an infinite number of solutions. So if you try and eliminate one of the variables from the three equations, what you will end up with is two equations that are in fact identical. So the example we had, I think, was 5x minus y equals 13, and we had that again when we eliminated it in another way. So when you've got that case there, there's nothing you can do with that, because those two lines, as they are there, are the same line. You can't solve it, therefore it's a straight line, and you can give the equation of the line, of course, but there's not one solution for that. The final case is where you've got zero solutions, and what will happen if you try and solve that is you'll end up with equations which just don't make sense. They're not consistent. So you'll get a number here that is different to that one. And that the case we had before is 15 rather than 13. And it's like having two lines that are parallel to one another, they will just not meet. Okay, so you need to be able to solve systems where there's a unique solution, where there's an infinite number of solutions, and where there's a zero number of solutions, and you need to be able to say also which case it is. So if it's an infinite number of solutions, could you say whether it's the sheaf of planes or whether the three planes are coincident? Okay, stop the video now and try some questions of your own.